Chapter 9, Segment 3, pages 275 to 282. Two-tone suppression. The rate at which an AN fiber responds changes when energy is introduced at nearby frequencies. Two-tone suppression is a decrease in the firing rate of one auditory nerve fire due to a new tone when a second tone is presented at the same time. Suppression effects are particularly pronounced when the second tone has a lower frequency than the first one. Rate saturation. Sounds that matter most to listeners. Most conversational speech. Intensity curve. A map plotting the firing rate of an auditory nerve fiber against varying frequencies at varying intensities. Frequencies such as 1000 Hz, to which the AN fiber had almost no response at low intensity levels, evoke quite substantial responses when intensity is increased. Rate saturation is the point at which a nerve fiber is firing as rapidly as possible, and further stimulation is incapable of increasing the firing rate. The further stereocilia pivot, the faster AN fibers link to that hair cell fiber. If we increase the frequency to 1250 Hz, the firing rate increases, and it increases even more at 1500 Hz. The problem is that 1500 Hz, the fiber's firing maxes out. It saturates. The brain cannot rely on a single AN fiber to determine the frequency of the tone. Rate intensity function is a graph plotting the firing rate of an auditory nerve fiber in response to a sound of constant frequency at an increasing intensity. Low spontaneous fiber is an auditory nerve fiber that has a low rate, which is less than 10 spikes per second, of spontaneous firing. Low spontaneous fibers require relatively intense sound before they will fire at a higher rate. Low spontaneous fibers are more like cones, requiring more energy to start responding, but retaining their frequency selectively over a broader range of intensity. High spontaneous fiber is an auditory nerve fiber that has a high rate, more than 30 spikes per second, of spontaneous firing. High spontaneous fibers increase their firing rate in response to relatively low level sounds. High spontaneous AN fibers are somewhat compared to rods in the retina. They are especially sensitive to low levels of sound, responding at rates above resting level even when decibels levels are quite low. Mid-spontaneous fibers is an auditory nerve fiber that has a medium rate, which is from 10 to 30 spikes per second, of spontaneous firing. The characteristics of mid-spontaneous fibers are intermediate between low and high spontaneous fibers. Auditory systems can accurately determine the frequency of incoming sound waves by integrating information across many AN fibers and using the pattern of firing rates across all these fibers. Uses the same system as the visual system. The temporal code for sound frequency. Phase locking. Firing of a single neuron at one distinct point in the period of a sound wave at any given frequency. The neuron need not fire on every cycle, but each firing will occur at the same point in the cycle. May occur because AN fibers fire when the stereocilia of hair cells move in one direction but do not fire when the stereocilia move in the other direction. Temporal code is turning off different parts of the cochlea to different frequencies, in which information about the particular frequencies of an incoming sound wave is coded by the timing of neural firing as it relates to the period of the sound. Volley principle. The idea that multiple neurons can provide a temporal code for frequency if each nerve fires at a distinct point in the period of a sound wave but does not fire on every period. AN fibers with relatively high frequencies, CFs, encode lower frequency, energy, and temporal patterns of their responses. Auditory brain structure. The nerve fibers that make up auditory nerve share crane nerves 8 with nerve fibers from vestibular system. The cochlear nucleus is the first brainstem nucleus at which afferent auditory nerve fibers synapse. It consists of 3 subnuclei, contains many specialized neurons. The superior olive is an early brainstem region of which in the auditory pathway, where inputs from both ears converge, especially good at preserving accurate timing information. Some of the neurons that project from the cochlear nuclei to the superior olives cross over to the opposite side of the brain. Signals from both cochleas reach both sides of the brain after only a single synapse. Inferior colliculus is a midbrain nucleus in the auditory pathway. Neurons from the cochlear nucleus and superior olive. Medial geniculate nucleus is the part of the thalamus that relays auditory signals to the temporal cortex and receives input from the auditory cortex. It is the last stop in the auditory pathway before the cerebral cortex. Tonotopic organization is an arrangement in which neurons that respond to different frequencies are organized anatomically in order frequency. Neurons most responsive to low frequency energy lie on one edge of the structure, and is responsive to high frequency lie on the other. Responsive to other frequencies spread out in orderly fashion. Primary auditory cortex is the first area within the temporal lobe of the brain responsible for processing acoustic information. The belt area is a region of the cortex directly adjacent to the primary auditory cortex with inputs from A1, where neurons respond to more complex characteristics of sound. Parabelt area, a region of cortex lateral and adjacent to the belt area, where neurons respond to more complex characters of sound as well as to input from other senses. Psychoacoustics is the study of the psychological correlation of the physical dimensions of acoustics and is a branch of psychophysics. Carefully distinguishes between the physical characteristics of sound and the impression of these sounds for listeners. Sounds measured with frequency, but listeners hear pitch. Frequencies and pitch are interchangeably with intensity and loudness.